right, so we are going to look at 11.2, which is what we call a finite and infinite series. So we've already talked about the notation that we use for a sequence. Okay, the difference between a sequence and a series is just a list of numbers. A series is when you add up the list of numbers and get an answer. So generally, remember, sequence is written with a lowercase English letter. So that formula is a formula for sequence A. And the N stands for the position that you want to figure out. So if you want to know the number that would be in the 12th spot in this sequence, you'd fill in 12 for N, do it out, and that would be your answer. Okay. So let's write out the first, 4 or 5 terms. If I plug in a 1 for N, what would I get when I do out what's on the right-hand side? Let's see, 2 times 1 is 2, minus 1 is 1 squared. Yep, which would just be 1. I'm going to leave it as 1 squared for now, but yes, it would be, I'll put the 1 underneath it. How about if we plug in a 2? What do we get? 9. So you get 2 times 2 is 4, minus 1 is 3 squared. So I'm going to leave it like that for a minute, but I'll also put the 9 underneath it. How about if you plug in 3? Yep.
25.
Yep, so we get
Or
2 times,
squared.
yep, 2 times 3 is 6, minus 1 is 5 squared. I think if you write the pattern squared, you'll see what it is quicker. And let's just do one more. If you do 4, plug that in, yep.
7 squared.
7 squared. So basically, this is odd numbers squared. That's the pattern. Odd numbers squared. So now what I'm going to look at is adding these numbers together. 1, 9, 25, 49. And what I'm going to do is I'm going to start by adding just the first number. Then I'll add the first 2. I'll add the first 3. And then I'll add the first 4. And we're just going to write down those different answers. So the notation that we're going to use is, that's an S, not a 5. S sub n. S stands for the word sum. So S sub 1 means to look at what I have circled in purple and add up the first 1 terms. Well, if you take what I have circled in purple and you add up the first 1 terms, all you get is 1. How about S sub 2? That means to add up the first 2 terms. What do you get if you add up the first 2 terms? Yeah? 10. You add up the 1 and the 9 and you get 10. 10. S sub 3 means to add up the first 3 terms. What do you get if you add up the first 3? Yeah? You get 35. I didn't have F sub 4, but we can just put that one in right there. What do you get if you add up the first 4 terms in that sequence? So 35 plus 49. 84. Yep. Any question how we got these numbers I circled in purple? 1, 10, 35, 84. So now, if you take those numbers and put them in a sequence. 1, 10, 35, 84. That is a new sequence. That's called a sequence of partial sums, where this represents the sum of the first 1 terms, the first 2, first 3, first 4 of the original sequence that I gave. Okay. So now the goal would be to figure out a pattern in those numbers. If we can figure out what the pattern is, 1, 10, 35, 84, then we can add up as many as we want without even having to find them. Okay? Because finding them and keep finding them and adding them up is going to take too long. Okay, what if we want to do that for the first 400 terms? We don't want to have to find all 400 and then add them up by hand. Okay? So we're going to try to find some patterns with those sequences. Okay, the sequence of partial sums. So our particular sequence, if I wrote it out, would look like this. We had 1 squared plus 3 squared plus 5 squared. This one added 7 squared. I would keep adding odd numbers squared until I finally get to the last one, and then I would stop. Okay, whatever the last one was. The last one that we did, n happened to be a 4. That's where I stopped. That gave me 7 squared, and that was this one. I didn't write it. I could have written it out. But what's going to be important about everything we add up today is it is going to stop somewhere. It's not going to go on forever. So even if something went on for hundreds of millions of numbers, you can add them all up. It may take a while, or you might have to figure out a way to do it. But you can always add up a bunch of numbers that you know stop. Okay? It's when they go on forever, then we'll look at it tomorrow. Okay? But today, it's always going to stop. So each one of these numbers, the 1, the 10, the 35, and the 84, those are each called a series, because the way we got those numbers was from adding things together. And anytime you add items together, that is a series. We didn't write 84 as 1 squared plus 3 squared plus 5 squared plus 7 squared, because that's going to take a long time to write it. We just wrote the answer, 84. But you can't forget how we got it. This is how we got it. It was the sum of 4 terms added, 4 numbers added together. Okay, so again, the idea of finite means that it ends. Right? Let's back up. Each one of these terms was created by adding up a specific amount of items. 1 item, 2 items, 3 items, and 4 items. If we wanted to know what the items were that we added to get these numbers, well, then you'd have to look back at your original formula that gave you what we had circled in purple right here. So what I wrote right here was this. That was S1, the sum of the first 1 terms. This is S2, the sum of the first 2 terms. This is S3. That is S4. We can go as high as we want. We can add up whatever number they want us to add up. And here's the same idea, it's just written more generically. Okay. If you had a sequence, S1 is really just the first term. So my first term here was a 1, and that's all I have. There's nothing to add to it. S2, you add the first 2 terms, whatever they are. In my case, it was a 1 and a 9, but it could be any numbers. S3, you add the first 3 numbers in your sequence. Mine was a 1, a 9, and a 25. Okay. And S sub n would represent adding n terms together. Now, when you have something like this, you don't know how many terms n is. It could be 100, could be 1,000, could only be 2 more. Who knows? But again, the point is it stops. We don't know where, but it does stop somewhere. What would be on the end of this if it went on forever? Yeah? Yeah, you'd see another ellipsis on the end. So when you see something like this, that means that it doesn't stop at a sub n. It continues forever. Okay. But you're not going to see that on the end of any problems we do today. Okay. And the kind of the goal of this section is to figure out a formula for that. How can you find the nth partial sum without actually adding up every single number? Okay. It's not not bad if you only have to add up 2 or 3 numbers, but again, if you got to add up 50 of them, I don't want to find them all by hand. It's going to take too long. And the chance of me making a mistake is pretty good. I have to find 50 numbers and add them all up. Probably with a calculator, I might make a mistake. So even just writing this down, like if I said to you to find S sub 50, well, even just writing it is going to take a long time. Never mind doing it. Just writing down 50 terms and putting 49 plus signs between them, that's going to take a while. So the first thing we want to come up with is, what is a faster way to just write down a way of adding up as many terms as you want? It doesn't actually give us a quick way to do it. It just gives us a quick way to write what we want to do. Okay? But at least it's something. It's a little bit shorter. And the notation that we're going to use when we want to write down adding together a lot of items is called sigma notation. So sigma notation has 3 parts to it. It has this thing on the bottom, which I'll talk about. It has something over on the right, and then it has something at the top. So it has 3 parts. This part on the bottom, we're going to think of this as kind of like a start value. It's going to tell you what number you should start with when you're plugging into your formula. This number is going to be a stop value. It's going to be where we're going to end. It's going to tell you the very last thing that you should plug into your formula. And this is going to be the formula that's going to create the things you're going to add together. So it's going to be the formula for the sequence. And this capital, that's a capital Greek letter, capital sigma. That symbol in math means to add together a bunch of numbers. That's what it means. And the way that you would read that is like this. It's the sum. That's how you read the sigma part. The sum from your starting point to your stopping point of, and then you tell me the formula that you're using to create all the numbers you're going to add together. Okay, I'm going to show you an example. Okay, we'll do one out, not a big one, just a small one. So we're going to add up 5 numbers. This is the formula that's going to add up. Well, that's the formula that's going to create the numbers we're going to add together. So the way that you get the numbers is you start with 1, you plug it in for k, and then you continue going up by 1 each time until you get to 5. And that's the last number we're going to plug in for k, and then we'll stop. Okay. So if we plug in 1 for k, what does that formula give you? Yeah, gives you a 5. That's the first number in our sequence, and it's the first thing that we're going to start adding up. So we have a 5. Plus, the next number we're going to add up is now we're going to go to 2. So plug in a 2 for k. What do you get if you plug in 2? Yep, 7. It's the second number. So again, it's a quick way of writing down that we want to add 5 things up. It's not actually a quick way of adding them now. We still have to write them all out for now. Okay, so now the next number we plug in is a 3 for k. What do you get if you plug in 3? Yeah, 9. Okay, gotta keep going till we hit this number. So now go to the next number, go to 4. What do you get if you plug in 4 for k? Yeah, 11. Now we got to go to the next number after 4, which is 5, and that's my end value. So that's what I'm going to stop with. What if I plug in 5 for k? Yep. 13. So this that I just circled means to do that. That's what it means. 5 plus 7 plus 9 plus 11 plus 13. And we could add that up if we wanted. Any question on how we started with this? This is called sigma notation. This is called expanded notation. How I changed it from sigma to expanded. One other thing I didn't mention, this number at the bottom that we're going up by 1 each time, that is called the index of your summation. It's called the index. Let me show you this. Let's go from 0 to 4. And let's do so it's going to be, let's do this. Let's do that one. It's the sum from k equals 0 to 4 of the formula 2k plus 5. What do you get if you plug in 0 for k? What's your first number? Yep, 5. How about if you plug in 1? Yep.
7.
7. What if you plug in 2 for k? Yep. 9. What if you plug in, what do we have? 0, 1, 2. Plug in 3 for k? Yeah.
11.
11. And now the last number, what if you plug in 4 for k? Yeah. 13. This and this are exactly the same thing. There's no difference. So what I did here, this is called re-indexing. I changed the index, but I still ended up with the same result. 1 is probably the most common index you would start with, but you don't have to. You could start with 10. You could start with 13 if you wanted. You do have to start with an integer. You don't start with a decimal. And the way that I figured this out is I brought this number down 1. I brought this number down 1. And then I took the k and I brought it up 1 to keep everything balanced. So like if I wanted to bring this down, like let's say I wanted to bring this down to a -1. Well, I'd have to bring this down 2. I'd have to bring this down 2. And then I'd have to bring the k up 2 to count to balance me bringing everything else down 2. Okay? So you might write something in sigma notation and you get a different formula than I do, but it could be equivalent. There's an infinite amount of ways you can do these kinds of problems. I think I already said that too. So that's, the top is what we call sigma notation, the bottom is expand. When you have to expand something, I would say generally do the first 3 terms. That's enough. And then jump to the last term. Because the last term is a number, but you might not know what number it is. Like in this case, n is a number. Could be a million, could be a billion, we don't know. But it's not an infinity symbol. So I know that it stops somewhere. So you want to show me that you could do the pattern for the first, say, 3 terms. Then we'll do an ellipsis, and then we'll say, OK, here's the last term. And that's how we'll show the expansion. Okay. So what do we get here if we plug in 1 for k? Yeah, 25. So there's your first term. How about if we plug in 2 for k? Yeah, 49. And let's do the next one. If we plug in 3 for k, we're going to get
81.
Let's see. 5 squared, 7 squared. Yeah, 81. Yep. Now, we've done the first 3, right? So that's enough. There could be a bunch more terms. And now let's do the last term. What are we going to plug in for the last, to get the last term? What do we plug in for k? Yep. N. Plug in n. So the last term is 2 times n plus 3 squared. That's how you expand it. Okay. If you know what n is, like we did in this one, then you can expand it out completely. And you don't have to use an ellipsis. You're only expanding 5 terms. I mean, I wouldn't give you something where you had to expand like 100 terms. Okay, so if it's small enough, you can do the whole thing out. If you don't know what n is, that's how you do it out. Yep.
If we don't know what n is, do we always do only the first 3?
Yeah, the first 3 is usually sufficient to demonstrate a pattern.
Okay.
Yeah. I think the book sometimes, they do the first 4, but that's fine. All right, so now I'm going to look at some different properties of summations. This is kind of like the rules for combining summations together. So let's say that we had 2 different sequences. Okay, the first rule that I'm going to show you applies to addition of summations. So we're going to look at that, and I'll show you an example with some numbers and see if we can figure out what that means. On the left side, you have 2 different sequences. And this formula on the left is saying you're going to add the sequences together first, term by term. And then once you do that, add the results. So let me show you with numbers. Let's let a sub k be the sequence 135, very short, simple sequence. Let's let b sub k be the sequence 2, 4, 6. I want to find that first. What is the sequence when you add A and B together? To add 2 sequences together, just add the corresponding terms together. The first term, second terms, and third terms. So what would be this sequence? A sub k plus B sub k. Yeah? 3, 7, 11. That's this part right here. Now, this summation symbol means to add what you just told me together. Add 3 plus 7 plus 11. So sum of these 2 sequences is the 3 plus the 7 plus the 11. That's what the left-hand side needs to do. And what do you get when you add all those up? Yep.
21.
Let's see. 21. Now, the right-hand side is a different way of getting the same result. It says to first add together all the numbers in sequence A. So if you want to figure out what this is, you're going to do 1 plus 3 plus 5. That's the sum of every number in sequence A. And what does 1 plus 3 plus 5 give us? Yep. Gives you 9. Okay. Now the second part says to take all the numbers in sequence B, because that's a B, and add, that's what that symbol means, add them all together. 2 plus 4 plus 6. Okay. And what does 2 plus 4 plus 6 give you? Yep. 12. And now there's a plus sign between the 2 values I just got. What's 9 plus 12 give you? Yep.
21 again.
21. So it's 2 different ways of getting the same answer. Any question on how the way on the left was different from the way on the right? Same goal, just a different way of doing it. The nice thing about this way on the left is it takes 2 different sigmas and combines them together into one. And that's what we generally, well, I guess it depends on the problem, but a lot of times you do want to take 2 sigmas and merge them together as one. But you can take 1 sigma and separate it into 2, just using these rules. Now, that rule works for addition. The exact same rule works for subtraction. I'm not going to do it with numbers this time. But the way on the left is telling you to find the difference between each term in the sequence, get all those answers, and then add them up. The way on the right is telling you to basically do what we did up above. Add up all the numbers in the first sequence, add them all up in the second, and then subtract the results. Again, just another rule for taking two sigmas and combining them into one, or taking one and splitting it into two. Okay, and the last rule. The last rule has to do with multiplying a sequence by a constant and then adding up the results. There's two different ways you can do it. Let me show you the way on the left. So sequence A is 1, 3, 5. C stands for constant. Okay, C is just a number. Okay, it could be any number you want. I just made up 4. Okay, let's pretend C is 4. If you want to find C, or you want to find a number times your sequence, think of distributing that number to every term in your sequence. Right, that's how you do it. So in our case, 4 times sequence A. What do you think would be my new terms if I found 4 times sequence A? Yep.
Would it be 4, 12, and 20?
Yeah. That's 4 times my sequence. 4, 12, 20. That's this part. Now, sigma means add up the numbers that you just said. 4 plus 12 plus 20. And what do we get if we add 4, 12, and 20 together? Yep. 36. Now the way on the right. The way on the right, you do the part that I circled first. Add up every number in sequence A the way it is. Okay, don't change it. So C is 4. And what do we get if we add up 1, 3, and 5? Yep.
You get 9.
Get 9. That's the sum of every number in sequence A. And then the 4 is in front of it. What's 4 times 9? Yeah. 36. So you get the same answer. The second way is probably easier because you only have to do one multiplication. You add everything up first, you multiply when you're done. The first way, you have to distribute the multiplication to every term in the sequence and then add it up. This way would generally be easier to do. But it's the same result. Okay. Any question on that? Yeah.
For all these to get to the safe start, K equals 1.
Yes. Yeah. So I should mention that. Whenever you're working with these formulas, they have to start at the same place, stop at the same place. You can't have like if I gave you a K equals 2 to N and a 1 to N, and I wanted you to merge them together, you can't do it if the bottoms are different. You would have to fix the bottom one to be a 1 like I showed you. You'd have to re-index it. Probably not something you're going to have to deal with, but yeah, good question.
Are we ever going to not get given the K?
No, every problem will give you the start and the stop. Yeah. If it wasn't there, then yeah, the problem would be incomplete. Okay, so I want to combine these two summations into one. When we merge them together, what is going to be our start value for the index? know it's kind of getting at the question that was just asked. I merge them together. The new start value for the new summation that I'm about to create is going to be, has to be the same as the originals. It's going to start at 1. And the summation is going to stop at the what term? Yeah, nth term. It has to stop at the nth. And now we just need a formula that's going to combine them. It's basically just combining all the like terms together. This is a sub k. This is b sub k. So all you have to do is find what do you get when you add a sub k to b sub k and put the answer next to your summation. Anyone think they could tell me what you'd get when we put those two summations together? Yeah.
6k squared is 2k plus 3.
And then plus 3. So 5k squared plus 1k squared. Negative 2k doesn't have any like terms, and negative 4 plus 7 gives us 3. Any question on how we combined two sigmas into one? And that would probably be a little bit easier to work with than having two, because now you just have one formula to have to deal with rather than two separate ones. But it still doesn't give you a quick way of doing it. Even if I just said to you, I want you to do this summation for k equals 1 to 20, unless I show you a trick, which I'm about to, right now you would have to take the number 1, plug it in for k, do it all out, get your answer, write it down. Then plug in 2 for k, do it out. 3, 4, 5, you have to plug in every integer from 1 to 20. Write them all down, then you plug them in, and then add them all up. It's still going to take a while to do that. So that's the important thing to understand about sigma notation. It doesn't actually help you do anything faster. It helps you write what you want to do faster. So if we're trying to come up with a quick way of doing something, leaving a sigma in the final answer, not good. Because a sigma doesn't help you do anything fast. So we got to figure out a way, when we have a problem like this, how can we actually get rid of that? What can we do to make that go away? And in general, that's not easy to make go away. For some things it is. In this problem, it would be, because you're only dealing with things that are squared, linear, and constants. We could make this sigma go away pretty easy. But depending on what your problem involves, it might not be as easy. Now, sometimes you can kind of come up with tricks, like this problem. It's basically saying to add up every number from 1 to 10. That's what that notation says. Anybody see a clever way you could do that? Clever way to add up all those numbers. And if you wanted me to do 1 to 100, I could do it just as easily. Not really getting into anything with formulas yet. It's just if you're clever, you might notice this. Yeah? Yeah. Yep, that would add up to 55 if you add up every number from 1 to 10. So looking at it as pairs, you have an 11 if you add those two numbers together. And then you have another 11 with a 9 and a 2. 3 plus 8 is 11. 4 plus 7. And 5 plus 6. You have 5 pairs of 11s, so that adds up to 55. Well, that's great if you notice that trick, but we can't always come up with a trick like that for every problem. But that's going to work for this one. So we need a way that's going to work for more things in general. So I'm going to show you some formulas you can use to get rid of the sigma when you have a linear formula, which is what that one is, it's just k to the first. I'll show you one you can use for a quadratic, and I'll show you one you could use for a constant. I have one for a cubic, but I'm not gonna show you that one. All right, so let's make a table and find some nth partial sums and see if we can come up with a pattern. So what we're going to do is we're basically going to look at something like this. This thing circled in purple. And I want to find a pattern for those numbers. That's the goal right now. Find a pattern for those numbers. We're going to use numbers that I think are a little simpler than that. So maybe you'll see a pattern. Maybe not. So this is the same problem I just had written down. You're adding up every number from 1 to n, and all you have to do is fill the number in for k, so it just becomes the number. There's nothing else to do. So what would you get if you add up the first 1 terms in that summation? Yeah, yeah, you just get 1. Okay. What if you add up the first 2 terms? Yeah? 3. Yeah, I get a 3. How about the first 3 terms? Yeah?
6.
Yes, 6. And the first 4 terms? Yep. 10. Okay. First 5, we get, yep, 15. First 6, 21. And we'll do one more. How about if you add up the first 7 terms? What's in that box right there? Yeah, 28. Okay, so now look at the numbers that are circled in purple. We want to find a pattern for those. If we can figure out a pattern somehow involving using that number to predict that number, then all I have to do is take that number, plug it into some kind of formula, and it'll automatically give me that number. Because right now, if I said, what do you get if you add up the first 605 terms, I don't know if anyone would know how to figure that out without actually listing all 605 terms out. Well, first of all, is this arithmetic? 1, 3, 6, 10, 15, 21, 28. Is it arithmetic? Really? Yeah, how come?
It's the base number plus the
That's not the definition of arithmetic. What does it mean if something's arithmetic? Yeah.
You take the base number and then you add the common difference.
Okay, so is there a common difference here?
No.
No. Common arithmetic means you are adding the same number repeatedly. To get from 1 to 3, you add 2. So are we adding 2 each time? No. We're not adding the same number over and over. So it's not arithmetic. Is it geometric? What would it mean if it was geometric? Yeah.
You can take the previous term and multiply it by the same thing.
Right, we're multiplying by the same thing. So let's see, how do you get from 1 to 3 if you use multiplication? You times by 3. So are we timesing by 3 each time? 3 times 3? No. So it's not arithmetic and it's not geometric. It's neither of the kind of sequences that we studied so far. So it's something else. Did anybody see what kind of pattern it is? Yeah?
You have to like multiply it by the next n, so like, or add the next n, so it's like 1 plus 2, and then 3 plus 3, and then 6 plus 4, and then 7 plus 5, and then 15 plus 6, and 21 plus 7.
Okay, so that's what's happening recursively. So then what would, if I went all the way down to 600, goes right there. Because you need to know the 599th one. If we knew that one, then yes, we could just take 21, add 7, and get 28. Take the 599th one, whatever it is, add 600, and then we get that. But that relies on us knowing every number up to 599 to do that. So that is what's happening, but we got to figure out a different way.
Something like 1 plus 0.5 times n, because 1 times 1 is 1, 2 times 1.5 is 3, 3 times 2 is 6, so it increases, it multiplies by 25 more per set. Does that make sense? So like 600.
So like 1, 1.5, 2, 2.5 kind of thing. Okay, I kind of see what you're talking about there. So we gotta kind of explore that idea a little more. So let's write those numbers down. First of all, this is going to be a polynomial pattern. I'm not telling you what degree, but it will be a polynomial. If you know something's going to be a polynomial, there's a trick you can use to figure out the degree. What do you get if you do 3 minus 1? Yeah? 2. How about 6 minus 3? Yeah? 3. And 10 minus 6 gives me, what does that?
4.
4. So what we're doing here is we are finding what are called the first differences. These are the first differences of my original sequence. Now I want to find the second differences. So do it again. What's 3 minus 2? 1. And 4 minus 3? Yep. 1. We're going to get all 1s. These are called my second differences. How many times did I have to do this process of finding differences before I ended up with a row of constants? Twice. That means this pattern is going to have an exponent of 2. And if we have a polynomial and the highest exponent is a 2, what kind of polynomial does that make it? Yeah?
Quadratic?
It's a quadratic. So this is a quadratic pattern. So it involves something squared somehow. All right. The calculator can help us figure out what the pattern is. Now that we know it's a quadratic, if we press stat, the calculator can automatically look for quadratic patterns. As long as it turns on, that's a key for this whole thing to work. Let's just walk over here.
I apologize for the interruption. Girls o'clock.
Okay, so we're going to type these numbers into the calculator. And if you go to stat and you go to calc, the calculator can look for quadratic patterns. Okay, now that we know it's a quadratic, we're going to put those numbers and tell the calculator, try to find a pattern. So first I got to put all the numbers in. So I'm going to press stat. Then the first option I see is edit. So I go to edit. And what I'm going to do is put all the left numbers, the 1 through 7, put those in L1. So 1, 2, 3, 4. That's probably enough. I can put them all in. It's not going to make a difference. I'm going to press my right arrow. And now I'm going to put different numbers in L2. I'm going to put in the 1, 3, 6, 10. So 1, 3, 6, 10, 15, 21, and 28. Okay, so we've got all the data typed in. I think we've used this screen before. Way at the beginning of the year, we did something with this. But what I'm going to do now is tell the calculator to try to find a quadratic pattern. So go to stat, go to calc, and the fifth option down is what we call a quadratic regression. So it's going to try to find a parabola that goes through those points. And it's going to tell me the equation. So press 5. As long as you did it the way I did, where you put your x's in L1 and your y's in L2, you don't have to adjust anything on that screen. Go to calculate. And it gives us a formula. All right, so let's write that down. It gives you the type of equation up at the top, and then it's telling you values to plug in for A and for B. So it's telling you that the formula is 0.5, and we're going to use the letter n because we don't use x when we talk about sequences, so I'm going to use n. N squared plus 0.5n. Now that's going to work, but that's kind of hard to think about in my head. So I want to make this a little bit simpler. What can I factor out of both of those? Yep.
0.5.
Yeah, let's factor out 0.5. Okay, that's going to make it a little easier to think about. Now, multiplying something by a half is the same as dividing it by what? If you take half of something, you could also just, let's just divide it by 2. So that's one way you can write the formula. And then sometimes what they do is they also factor the n out of the top. You could do it either way. Same thing. I think that's how the book does it on the right, but this way works perfect as well. Let's try this and see if it works. So let's take this formula. Let's plug in a 6 and see if we get 21. What's 6 squared? Yeah.
36.
36 plus 6 is how much?
42.
42. And what's 42 divided by 2? 21. So when you plug in 6, you get 21. Okay. Let's try another one. Let's try 4. If we plug in 4, let's see if we get 10. 4 squared is 16 plus 4. 16 plus 4 is 20. 20 divided by 2. There we go, 10. So now, if I said to you, what do the first 600 terms add up to? It's easy. Just do 600 squared, add 600, and divide by 2. There, I need a calculator, but we could do that out and get the answer. So any question on that? So now that we know this formula, we're not going to, or this version of it, whichever one you want. Even this version is fine too, if you want to think of it that way. I usually think of it this way. They're all the same. Okay, so I'm going to show you some different formulas now that can take something that has the sigma, get rid of the sigma, and turn it into a formula like that. Okay? We're not going to go through deriving the formula on the calculator every time. I'm just going to give you the formula. So we're going to look at some formulas that basically get rid of the sigma and allow us to substitute in a formula to do it quickly. Let's start with this. This one's kind of a special case. But once you understand it, it's actually the easiest one. This means to add up a constant number n times. Let's say I wrote down this. That means to take the number 1, plug it in for k in this formula, and then write down the answer. So what do you get if you take 1, plug it in right here for k, and then do it out? What would you get? Yeah?
8.
8. And do it again. Take 2, plug it in for k, and what would you get when you plug in 2? Yeah.
16. Oh, okay.
Nope, 16. Plug in 2 for k right here, and tell me what you get. Yep, 8. Now take 3 and plug it in for k right there. What do you get? Yep, 8. And now we're at the last one. Plug in 4 for k right there. What do you get? Yep, 8. You're adding up a constant that many times. There is no k, it's a constant. So what would be a quick way of doing that out? Yep. 8 times 4. So what do you think the formula is going to be for this? It's not 8 times 4 because that's a specific example. Yep. C times n. Yep. So you're just adding up a constant n times. So that is the quick way to get rid of a sigma when there's a constant. This is the formula that I just went over with you guys. This is adding up the first n integers. 1 plus 2 plus 3 plus 4 plus 5 plus 6. We just looked at how to do that pattern. And this is the formula we had. Or it was one version of it, all fact. N times n plus 1 over 2. Now, the next one is a formula for adding up not the first n integers, but the first n perfect squares. Like 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, as long as you want to go. Now, when we added up a formula that was linear, the answer was a quadratic. Because if you distribute that out, it's going to be n to the second power. Now we're adding up terms that are generated from a quadratic formula. What kind of exponent do you think we would have over on the right-hand side in the formula that would simplify this? Yep. So this had an exponent. What's the exponent on this? 1. And what's the exponent on this? What's the degree if you do it all out? 2. So now the exponent on this is a 2. So what do you think the degree would be over here? 3. It would be a 3. So if you wanted to add up, say, 1 to 100, squaring every single number, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, all the way to 100 squared, all you have to do is fill in 100 for n and do it up. Okay, so those are 3 formulas, and the only 3 that I'm going to show you for getting rid of sigma notations when your terms are a constant, generated from a linear pattern, or a quadratic pattern. Okay, there's one for k cubed. Don't worry about k cubed. You can probably guess it is a 4th degree exponent when you do it out, but 1 through 3 is enough. Okay, so let's see if we can simplify. You know what? I'm not even going to do the quadratic one right now, just to keep it simpler. Let's see if we can figure out a formula to do this. I want to add up the first n calculations in the formula negative 2k plus 3. If you don't understand how to get rid of a sigma, then the way you'd have to do this problem is, let's say n was 500. Plug in every number from 1 to 500, one at a time, for k. Write down every answer you get when you do that, and then add them all up. I don't want to do that. I want a formula that I could just plug the number 500 into and just get the answer automatically. That's what we're figuring. So let's start by looking at this and see if it matches anything over here. Does what we have in example 3 directly match what's in any of those boxes? Really? No. We have to break it down until we get it to look a little bit simpler. Let's start by breaking it into 2 different sigmas. Where is each summation going to start? That's what's going to be my starting index. Yeah. They both have to start at 1. And where will they stop? Yep. They both have to stop at n. And what's going to be the formula that goes in the first summation? Negative 2k. What's going to be the formula that goes in the second summation? Yep, 3. And what are we doing with the 2 summations? What symbol goes between them? Yep, addition, because this is addition right here. Okay. Now, so now we've got 2 sigmas, but they're each a little bit simpler than the first one. Does either one of these sigmas match something that's over here? Yeah.
The second sigma matches the first one.
Right. This right here is rule 1. You're adding up the number 3 n times. So what's a quick formula that would add up the number 3 that many times? Yeah. 3n. So we got rid of that sigma. That one's gone. So we've got 3n. And now that second one, well, it's really the first one. This one almost looks like which one? It's linear, but it's not, it's something with it we really don't want there. Yeah? It almost looks like the second one. What's making it not the second one? Yeah? Right, there's a negative 2 being multiplied by the formula that's generating the sequence. What are we allowed to do with that negative 2? Yeah? Yeah, you can put the negative 2 in the front. That was a rule I showed you right here. That number can go in the front. And once we do that, it's going to match what we need. So let's rewrite it. So it's negative 2 times the sum from 1 to n, k. And we already dealt with the second one. That one's gone. Now we can deal with this. What's the formula for adding up the first n integers to the first power? Yeah. Well, it's not this one. We're adding up the first n integers to the first power. What's the formula for that? Yeah.
N times n plus 1 over n.
Right. This thing circled in blue turns into this. That's the quick way to do that. Times negative 2 plus 3. And now we just have to clean that up and combine like terms. So multiplying by 2 and dividing by 2 is going to cancel. We have to distribute that negative. So that's negative n. Well, actually, let me do it like this. Let's distribute the negative n there, and then the negative n there. So that's negative n squared and negative n times 1. Any question on how I distributed that? Both the negative and the n have to get distributed. And what would I get for final answer? Yeah.
Negative n squared plus 2n.
Negative n squared plus 2n. So now, if you have to add up the first, 500 numbers in this formula, you don't have to plug in every number from 1 to 500 now and add it all up. Just plug in the number 500 here and there, and you'll get the answer automatically. So you want to look for a summation that's going to look like one of these three. And that's how you do it. It might be helpful to keep this done out because you're going to have to distribute it every time you use it. Same here. A better version might be to FOIL that all out. Then you don't have to do it every time. Okay. Any question on that? All right. So last thing. If I have this, what kind of pattern is that? I'm only giving you 3 terms, but it's enough. Yep.
What's the last number?
18.
Okay.
Sorry, yeah, if that was a 10, that looked very confusing. Yeah. It's geometric. It's geometric. Now, these formulas that I just gave you right here, none of them are geometric. So what if I want to add up numbers that fit this kind of pattern really quick? Well, there's a formula to do that too. I'm not going to do that one. And that is the formula. So if you want to add up, let's do the one that I just had. What did I have? 2, 6, 18? Yeah, I could add that up myself really easily. 2 plus 6 is 8, 8 plus 18 is 26. Let's try this formula. What's the first term in this sequence? Yep, 2. And the R value is what I'm multiplying by each time. What do I multiply by to get from one number to the next? Yep, 3. Let's plug those numbers into that formula and see if we get 26. Okay, it should be 26. Okay, and this only works because this is geometric. This formula is only for geometric, and that is geometric. So first term is 2. R is 3. And how many terms am I adding together? Yep. 3. It's just a coincidence. The number of terms is 3, and I'm multiplying by 3. And we say R was 3. Let's see if that's 26. 2 times. What's 3 cubed? Yep. And 1 minus 27? Negative 26. 1 minus 3 is negative 2. 2's cancel. Negatives cancel. There you go, 26. So this formula, not useful for that, but if you had to add up a lot more numbers, will quickly add up all the numbers in a geometric sequence. Homework is 1 through 10 and 13 through 17. So you're basically skipping 11 and 12.